A very good morning to everyone. We have already conducted three webinars in the month of June, which started from the first one as the electrical fire in hospital. The next one was on the functional earthing, and the last one was the electrical safety of lift as per IS 17900. The topic for today is the cable sizing for low voltage electrical installations. And the speaker for the day is Krish Theobald, who is the Technical Director, Protego Plus Electrotech Private Limited. We have with us the President of NFE, S. Gopakumar sir, who will be doing the opening remarks. Krish Theobald is the technical director of Protego Plus Electrotech Private Limited. He is a meticulous and electrical designer specializing in LV electrical installation design for commercial and large scale domestic projects. He ensures on the ground compliance with national wiring regulations, particularly focused on electrical safety in India. Krish is recognized as a subject matter expert and contributes to Bureau of Indian Standards Committees ETD 20 and ETD 50. He also trains for BIS capsules course on the National Electrical Code of India and has conducted various training programs on topics like electric shock protection and selection of wiring systems and protective devices. Krish has authored articles and blogs, including contributions to the EMA journal, and has appeared in media such as FX and Hit, the Lights podcast in the UK. I would now request Gopakumar sir to give the opening remarks. Over to you, sir.
Thank you very much, Arya. Participants, today we are going to have an important subject, webinar on another important subject. First, let me introduce about NFE. Most of you know NFE very well, but still my job is to introduce it again. We are a passionate group of engineers in the field of electrical safety. NFE is a registered society. We registered, you can see the date here, 15th of August last year. So we are a not-for-profit organization. We are a new organization registered during last year. The vision of NFE is to make Bharat electrically safe, and we have the mission as train and develop skill and competency or competence in engineers or practicing engineers in order to make the nation safe. We have over 1,200 engineers at the moment as our members, and we are actively supporting standards, Indian as well as the international standards. We are creating awareness across India through various programs, seminars, workshops, and weekly webinars. Weekly, we are coming out with every week we have a webinar on some subject, and most of these webinars are participated by over 200 or sometime even 500 participants. So we also have some kind of training and certification programs. So an example of some of the programs which we already conducted. The first training program which we are planning is, or which we already launched, is a professional certification scheme based on ISO 17024. Here, the NFE certified electrical consultant, NFE certified electrical installer, and NFE certified electrical safety verifier, these three positions will be held. Through this scheme, professional certification scheme, we are trying to define who is a skilled person or who is a competent person to carry out design, installation, and safety verification. NFE is the scheme owner. We are making the rules. and we approve personal certification bodies. We are happy to inform you that the first personal certification body is already registered, already approved. Now, candidates can start applying if you are willing to go for, or if you are willing to have a certificate or like a recognition, like a NFE certified electrical consultant or installer or safety verifier. The links are available in our website. You can go to the website and you can apply if you are interested to participate in an examination and written and practical examination. Similarly, we are also making fault loop impedance testing professional. This is not an ISO 170 system, but this is a small level training system. The training will be carried out by NFE. Test also will be carried out by NFE. We have 3 levels of approval for flight FLIT professional. Level 1, you can see in the screen, level 1 engineer or level 1 professional is qualified for LT residential houses up to 15 kilowatt connected load, or with an MCB OCPD of up to 63 amps. Here, there is no qualification required. Anybody can apply. The application registration and application training charges are just 500 rupees. Once when you are registered, NFE will carry out training. Then there will be a theoretical examination. Those who are participating, passing the theoretical examination, they have to come to a common place, probably Delhi, Mumbai, Chennai, Bangalore, or these cities. We will conduct a practical examination. So those who are passing the theoretical as well as practical examination, we will be issuing the certificate, NFE Certified Fault Loop Impedance Testing Professional, Level 1. So please note that you need to have a meter for doing it. Either you have to have your own meter or you can hire, you can rent a meter, because during the practical examination, you have to show the meter. You have to do the test with your own meter. You can rent a meter. The current rating of the test instruments shall be 20 amps. So minimum is 20 amps. The second level, level 2 engineer or level 2 professional, will be capable of testing circuits up to 125 amps, basically a residential or commercial building up to 60 meters, up to 125 amp circuits you can make. And here there is a qualification requirement. It is for engineers or diploma holders with 6 months experience. This is not specific for electrical engineers. Any engineer or diploma holder will be able to apply for level 2, and the candidate should have a meter, 35 amps test instrument with the type AC and a type A RCD testing. So additionally, you have to have a meter of this quality. Either it can be your own meter or you can hire a meter for applying. The registration fees is rupees 1,000 and examination charges are rupees 1,000. Please note that we have put per examination. The purpose is, if the candidate fails the examination, theoretical examination, then he has to pay again and he has to attend the examination. For conducting this program, we have a committee, and the committee will decide and committee will carry out the test and the examination. For level 1 candidate, those who wanted to apply for level 2, they can do it by additionally paying rupees 500. The last one is level 3 FLIT professional. They will be qualified for doing test in all kind of buildings. The qualification required is engineers or diploma with a 2 years experience. The instrument, what they have to keep is they have to have a meter of 200 amps test instrument, and with the instrument also should have facility to test type AC, A, F, and B RCDs. Please note that even though the name is written as fault loop impedance testing professional, the actual job which he is supposed to do is not only fault loop impedance test, but here in level 3, we are covering a lot of additional safety measures. Almost all fault protective measures are included in level 3. During the examination, they have to write the examination and they have to prove they are capable of doing. The level one candidate or level two candidate who has already passed the examination of level two, they can, sorry, there is a small mistake. Level two candidate will be eligible to attend level three by paying rupees 1,000. So these three levels we already started. We already have about 50 plus registrations. The training will be starting probably by next week onwards. So if you are interested to become a FLIT professional, you are welcome. Please note that several organizations, including, for example, the some of the petroleum companies for verifying their petrol pumps, or banks for their branch offices, ATMs, they have approached us to make this qualification as quick as possible so that they can put, for example, level one engineer for ATMs, level one engineer for bank branches. So this is becoming serious now. You can also find a lot of technical information in our website. We have a blog where several technical informations are available. Also, under home, you can find out publications. There also a lot of information is provided. We are also coming out with our mass awareness program for college students, engineering college, as well as schools. Most of you are aware that this program is initiated and supported by CEA and BIS. We inaugurated the program last week. We also launched the book in English last week, 26th of June. Now the other translations are going on. We will be coming out the book with multiple languages. Then videos based on the book is also under preparation. So probably we will be kickstarting this program very soon. First year we are trying to cover 250 engineering colleges and 2,500 schools. So this is all about NFE. If you wanted to become a member of NFE, I request you please visit our website, and you can very easily become a member. So with this short introduction about NFE, I would like to invite Krish for his presentation on selection of wires in low voltage installation. Over to you, Krish.
Yeah, hi. I'm audible.
Yes.
Brilliant. Okay, let me just share my screen. And the screen is visible as well, yes?
Yes.
Brilliant. Okay. Okay, so before we begin, my name is Krish Theobald. We're talking about cable sizing for low voltage electrical installations. So, let's begin. So the subject for today is quite a pertinent one. So I'll just give you an overview. So when we select the size of cables that we use for our live conductors, there are a variety of factors that we have to take into account. The most common one that we talk about is temperature, and that's directly related to the current carrying capacity. So when you talk about normal operating temperature, it is temperature the cable's insulation can handle um, without being permanently damaged, and particularly steady state, where it can run at steady state. Then we have limiting temperatures, which is during a fault, what is the temperature of the cable? Again, to do with the insulation. Voltage drop, how much voltage drop can we possibly allow? Any electromechanical stresses that can occur due to overcurrents, especially short circuits in your single core cables can move around quite a bit. Any other mechanical stresses the insulation is subject to? Uh, Most of our installations are protected by the measure of automatic disconnection of supply, and there the earth fault loop impedance value is very important. Now, we've been talking about testing earth fault loop impedance quite a bit, but very important also is that it has to be the installation has to be designed keeping in mind these earth fault loop impedance values, and of course, the method of installation is also relevant. See, when we design an electrical installation, there are a variety of stages, but there are four stages that are quite pertinent to cable sizing. Well, other conductor sizing. First thing is we select our cables for current carrying capacity. Let's say let's say 2.5 square ohm can carry 23 amps, so on and so forth. Then we adjust our cable size for voltage drop. So we say, okay, current carrying capacity is taken care of, but is the equipment that we're connecting going to get the right level of voltage? Once that's taken care of, we say, okay, is the cable, the cables, now the conductors are providing the right current carrying capacity, they're providing the right voltage. But now the question is the earth fault loop impedance value low enough such that if there is a fault between a line conductor and a P and or a line conductor and a exposed conductive part, that when the fault occurs, disconnection of the protected device will occur in the required time. Okay. Once that is taken care of, we have to see, okay, when there is a fault, there is a certain amount of prospective short circuit current that is um, being that flows through the circuit. What happens to the cable? Can the cable withstand that amount of energy till the device causes disconnection? So these are the four basic stages that are there. So when we talk about normal operating temperature, it is the basically this has directly to do with the current carrying capacity. And current carrying capacity, the important thing is current carried by a conductor for sustained period during normal operation shall not cause the temperature of the insulation to be exceeded. Like I said, the important thing is the insulation. And 60364, the 60364 series and the National Electrical Code of India and IS 732, they're very clear that the current carrying capacities are this requirement, right? This is the requirement is satisfied if the current carrying capacity is selected and corrected in accordance with Annex B of 60364 or of course calculated one of the other ways is 60287 series. Important thing is that not only that do they have to be selected, they have to be corrected as well. That is a very important part. So yeah. Now when we talk about one second, let me just make sure if I want to do a laser pointer, it is nice and visible. No, never mind. Yeah, it's okay. Right. Now, there are two important types of insulation that we generally use on cables in low voltage electrical installations. There are four listed in this, but most of the times in electrical installations, we use either thermoplastic or thermosetting. Thermoplastic has a 70-degree conductor temperature, and thermosetting has a 90-degree conductor temperature. Again, remember, this is not to do with the actual copper or aluminum conductor. This is to do with the temperature the insulation can handle. And of course, where a conductor operates at a temperature exceeding 70 degrees Celsius, it needs to be ascertained that the equipment connected to the conductor is suitable for this resulting temperature. So, it's very popular to use thermosetting cable nowadays. It's cables with thermosetting insulation, especially for their fire performance and their smoke, the amount of smoke they emit. But it's very, that all the, um, unless we know that all the connected equipment, accessories, terminations, all connected electric equipment can also be able to withstand this temperature that exceeds 70 degrees, for example, 90 degrees. We cannot actually use a 90-degree current carrying capacity. We have to derate or use a 70-degree capacity, even though we're using a thermosetting cable. It's very important to keep that in mind. Now, how do we prevent an overload from occurring? Well, the first thing is conductors, loads, and overcurrent devices need to be coordinated. So we have IB shall be lesser than or equal to IN shall be lesser than or equal to IZ. Now, what does this mean? See, unfortunately, in practice, we have it's very often that we say, okay, this is the load current, this is the cable we choose. The protected device is chosen much later on. Unfortunately, that's not the right way we have to go about doing this. Let me give you an example. Was there a installation in Hyderabad, and IB, which is the design current, was about 100 amps. The cable was 35 square mm. Let's say after deviation set could also carry 100 amps, no problem. So you think, okay, it's fine. However, when I went and looked at the protected device, it was actually 630 ampere MCCB. So that protected device is actually providing no overload protection in any manner. So that's quite an interesting thing because we look at IB and we look at IT really, which is tabulated value. We don't even derate. We know how to coordinate. We know how to select a cable for a given design current, but we forget about the actual overload protected device. So that's an important consideration. So say if my design current was 100 amps, I would choose a device that had a value lesser than or equal to this. So say 100 amps again, and the cable should be able to carry after duration more than 100 amps. Now, I2 is another interesting value. So we know that if we have say a 10 amp device or a 100 amp device for that matter of fact, once the current reaches that value, 100 amps or 10 amps, whatever the rating of the device is, IN, the device is not immediately going to trip. In fact, it may not, if it's 100 amps and you have 110 amps flowing through, it's unlikely to trip at all. That's because these devices are designed with something called a conventional uh, tripping current or a conventional current causing effective operation. And these values are rated in multiples of IN. We, as electrical insulation designers, need to ensure that this value of I2 does not exceed 1.45 times IZ. So it does not exceed 1.45 times the derated current carrying capacity. Very important thing to take into mind. I'll show you a little later what that means. And just so you know, by the way, for an MCB, a 60898 MCB, I2 is 1.45 times IN. So if this equation is satisfied, this equation by default gets satisfied. However, when you use devices like HRC fuses or rewirable fuses, that's when we start to see problems with this equation. And I'll show you how to deal with it. Now, the important thing is when we have a tabulated current carrying capacity, as in, this cable can carry this many amps, that is often a very different from the effective current carrying capacity, which is the current carrying capacity in continuous service. Uh, so, quite interesting. Uh, if we look at the actual factors that come into play to go from IT to IZ, the standard looks at really four factors. Factor for grouping, so how many cables are actually grouped together. Factor for ambient temperature, whether the cable is in the air or the ground and what the temperature of the air or the ground is. Thermal resistivity of the soil, how the soil is able to dissipate heat. And the rating factor for devices with the fusing factor greater than 1.45. It's an HRC fuse. Okay. I'm not going to show you an example calculation for this because I keep showing it in all our presentations. So at the end, I will show you the factors itself, but at the end, if any questions are there, I can obviously show those slides because we have them ready anyways. The focus is more than just current carrying capacity today. See, tabulated current carrying capacities, when you look at our tables, there are a variety of factors to decide what value to choose, and not just what value, what table to choose as well. The material of conductor, so for example, copper in this case, the cross-sectional area, 1.5, 2.5, 4, 6, so on and so forth. What is the insulation? Is it the PVC insulation? And notice the subsequent temperature limits, 70 degrees. What is the insulation reference method? So A1, A2, B1, B2, C, D1, D2. The ambient temperature, so 30 degrees in air, 20 degrees in ground. And the number of loaded conductors, two loaded conductors. The idea really, again, is to make sure that um, we come up with the right tabulated current carrying capacity. You're looking at the right table as well. Grouping. So, how many circuits? Pretty obvious. What is the insulation reference method? Are the cables significantly loaded and are they equally loaded? And obviously the arrangements themselves. So, again, different tables, amongst the different tables, different values. Just to show you that there is a process to this as well. Ambient temperature. So, what is the ambient temperature? Again, most onerous. So, for example, if you go to some northern parts of India, it can get quite cool during the winters. So maybe it can go to even sub-zero. But during the summers, it can go to maybe 40. So just because 10 or 0 is the more favorable value doesn't mean you can take it because the most onerous, the cable should be getting the same amount of load in the hotter climate. So I would choose the most onerous value. The installation reference method. So, cables in air in this case. The insulation type, PVC, XLP, mineral insulated, so on and so forth. Soil thermal resistivity. If the cable is buried within the ground, the ability of the soil to dissipate heat matters a lot. The thermal resistivity of soil, obviously, in degrees Kelvin per meter watt. The method of burial. So in this case, it's a buried duct or it is a buried in the ground. Um, The buried depth, of course, if it's in a duct, these factors only apply to zero point 0.8 meters. Further allowances that we made if it's beyond zero point 0.8 meters. Now, the fusing factor, which is what I was talking about earlier. See, like I said, if a 10 amp device is there, once the current exceeds 10 amps, you're not going to actually have a device trip immediately. Or rather, if it's 11 amps, it's not going to trip at all in most cases. So, the most common devices we generally use are MCBs, MCCBs, and HRC fuses. So for an MCCB, this depends entirely on the setting we put. So that's not included in this table, obviously. But for an MCB, the 60898 device, 1.13, my apologies, 1.45 times IN, the device will trip within 1 hour. And what the conventional time and the conventional tripping current are defined in the product standard. And this is usually for a bunch of ratings. If you look at fuses up to 63 amps, it is 1.6 for 1 hour. Between 63 to 160, it's 2 hours. Between 160 to 400, 3 hours. Between greater than 400, it comes to 4 hours again. Yeah. So this is the relation here. Um, Again, we are concerned with the fusing current. So when there's a current equal to or excess of this value, then the device will definitely trip in the required
Krish,
time. Yes,
sorry to interrupt. Can you make it a little bit slow?
absolutely. Sure. So I will keep that in mind for the next slide. So I'll just explain this again as well. So, like I said, if you have a certain overcurrent protected device and the current exceeds that value of the nominal rating for an overload, the device will not immediately trip. So, for example, for a 10 amp device, if you have 11 amps flow through, in most cases, the device will not trip at all. So, there are two values, non-fusing or non-tripping and fusing or tripping. We are concerned with the fusing or tripping value, which means for a 63 amp device, 1 point or up to 63 amp device, 1.6 times the rating, the device will trip within 1 hour. Between 63 to 160, 1.6 times the rating, 2 hours, so on and so forth. For a 60898 device, which is our MCB, this is 1.45 and 1 hour. Now, these values are defined in the product standard. The only exception being an MCCB, because then you can set it and that depends on the actual setting. Now, important thing is what correction factor to use. Since we are allowed up to 1.45 times IZ, if the and IZ is generally equal greater than or equal to IN, since we are using 1.45 as the model value, sort of, if you're using an HRC fuse, we have to do 1.5 divided by 1.6 and you get 0.9, which means if you're using an HRC fuse, you can only utilize 90% of the current carrying capacity. Interesting to keep in mind. Okay, number of loaded conductors, something I want to talk about. This has more to do with harmonics, as we'll address later on as well. And I know some questions have come in about that as well. Um, See, current carrying capacity is conventionally defined for a variety of factors, one of them being loaded conductors. What this means is that for a single phase circuit, we're only considering line and neutral conductors being loaded. For a three phase circuit, we're only considering L1, L2, L3, or RYB as being loaded. In this case, if there is an unbalanced circuit for a single three phase circuit, and there's a current in the neutral, we need to take that into account. Deviation has to be applied because these values only apply for three loaded conductors. If you're in effect having four loaded conductors, that affects your ability of the cable to dissipate heat. Keep that in mind. Now, like I said, I'm not going to show you an example calculation because I keep showing it to you. But if there are any questions, I'll show. We can show that later on. Now, some interesting considerations that we need to keep into account. Conductors in parallel. See, it's very often that normally for a smaller circuit, we can just run one line conductor, one neutral conductor, one PE conductor. However, on much larger sites, it may not be practical to do so for size and for maneuverability. When we do this, we may have two runs. So, two line conductors, two neutral conductors, two PE conductors. And this is most common in, larger installations where you have, say, 630 conductors per phase. Primary concern here is each run going to be sharing the same amount of current? And I'll show you why. Obviously, the ratio of current sharing is very dependent on the impedance, is dependent directly on the impedance of the cables. This is not just the length of run, but also the spacing, and I'll show you what I mean. See, when you have larger single core cables, like I just said, for example, if you have 630 square conductors per phase, more than the resistance, the reactance is of concern here. When we have more than a 10% difference in current sharing, we need to consider each parallel run separate individually, not only for overcurrent, not only for overcurrent protection, not only for overload protection, for over short circuit protection. Then it's a question of, will a single protected device be able to clear a short circuit? I'll show you what I mean. And if we decide that each parallel run has to be protected, the best option is the linked OCPD, and I'll show you what I mean as well. See, When we look at conductors in parallel, like I said, supply, OCPD, load, right? Option A is you have a single OCPD protecting all parallel runs. Option B is we have an individual OCPD protecting each parallel run. Now, in this option, overload protection is provided for the entire circuit. However, if a single short circuit occurs on any one of these, what happens is that the OCPD has to be able to protect that individual run. So overload protection is for the whole, but short circuit protection is provided for each individual cable. So the requirements are very different. You have to basically consider an individual cable for short circuit protection. This is not the case, obviously, if an individual run is being protected by an overload protected device. If conductors are done in parallel, overall protection is provided for uh, well all of them. But we need to, like I said, make sure that the current sharing is equal, or because within 10% of each other. If not, we cannot actually have this first configuration. How do we calculate it? Well, for current A K I K, you can calculate it as the total design current multiplied by the impedance, the total impedance of all the conductors in parallel, divided by the impedance of this actual uh, run itself. And obviously, this is we all learned this in high school. We know how to do this. Simple parallel impedances. Obviously, because the impedance of all these conductors in parallel is going to be much lesser than the impedance of this run in particular. IB is the design current of the circuit. IK is the design current for conductor K. ZK is the impedance of this conductor K. And ZT is the impedance of this whole circuit. So all the conductors in parallel. Now, it gets particularly interesting when you look at short circuits, and I'll tell you why. See, what happens is that normally in a short circuit, there's a short circuit, disconnection occurs, circuit is dead. However, if there's a short circuit in this case over here, current will not only flow from this side to the short circuit, it will even this is just the line conductor, current will also flow back from here because current going from here will return like this, like this, like this, like this. So you have current flowing from all directions. That's something that interesting that happens. So the concern is that, well, if you have parallel, if this happens, yes, short circuit happens, disconnection occurs. If you have individual runs like this and individual protection of the individual runs, short circuit will occur here, current will flow. This OCPD may disconnect. This all these OCPDs may or may not disconnect. And the risk is if a current is flowing from the load side as well, and the point is that because of this increased contribution of fault current from the various directions or from the various conductors, the device may not actually be able to provide protection against short circuit for the conductors. I'll show you how we look at that later on, but just you understand the point I'm trying to illustrate is that there's a current flowing from all the parallel runs as well. The risk that can happen here is that, see, what will happen is that, like I said, current flowing from all sides. So we can then provide overcome protect device not only on the supply side, on the load side as well. However, there is another risk of doing this, which is that in this situation, current will flow from all sides. Current will flow through here. Disconnection will occur. This run goes dead. But now the other remaining runs are subject to an overload. And if this overload is such that it is between the fusing of the conventional non-disconnection current and the conventional disconnection current, this overload can go very it can go unnoticed basically. That is where it can go terribly wrong. So what is the ideal situation? The ideal situation is to have a linked OCPD. So if you have a linked OCPD, what will happen is that if there is a single fault, all of these are linked, so they will just trip. And it is very similar to have a single OCPD there. It is really the best and most ideal situation. Now, there are special considerations again because when we have single core runs, we generally use either unarmored or armored. More common is the armored aluminum wire armored conductors. If we consider unarmored cables, the current carrying capacities are tabulated for a certain spacing between the conductors. But when we increase the spacing, we are affecting the inductance, effectively the reactance. So as you space them out more, the inductance increases, the reactance increases, the impedance increases. However, if we space them together, they are in effect grouped. So the current carrying capacity is then reduced. So we have to strike a very close balance. If we're using aluminum wire armored cables, not only this concern is there is a question of do we connect the aluminum wire armor to the earth, to the peak and to the P at the load side or at the or at both sides, single point bonded versus bonding at both ends. Then we have to consider what is the voltage that is going to be induced in the sheath. What about circulating currents induced in this sheath? Look, I'm not going to go into too much detail about this. You can look at the 60287-1 series, and there is information also in certain guidance documents. If you have questions about this, you can take them separately. I had prepared a bunch of slides, but if you dig into this, it is really a can of worms that we are opening here. Voltage drop, like I said, under normal service conditions, the idea is that the voltage at the terminals of the equipment shall be greater than the minimum limit provided in the product standard. Now you will see in distribution systems, we also don't want to exceed the maximum limit. The standard says where in absence of this information, for a public LV or any specific information for the equipment, a public LV supply, we can only allow 3% voltage drop for lighting, 5% for other uses such as power. A private LV supply, 6% for lighting, 8% for other uses. Now, what does this look at? See, if we look at a single phase piece of equipment, our voltage drop is going to be affected by, if this is the point of commencement of supply, this is our distribution board, this is our load, the impedance of the line conductor and the neutral conductor. So in effect, the voltage drop is simply the design current multiplied by the sum of these two impedances. This is just the equipment. So how much voltage is dropped because it is being supplied through these conductors, essentially. Three-phase voltage drop, it is a combination of all three lines. So the design current multiplied by root 3 for the three-phase circuit for the sharing and the impedance of the conductors, because this is conventionally taken to be the same. So that's that. Now, how do we calculate voltage drop? There are two ways. I'll show you the easier and more conventional way, which is calculation of voltage drop on manufacturer data. So a manufacturer will say for a certain cross-sectional area of cable, whether it is a 2-core cable, 3-core, 4-core, 5-core cable, and how whether it is touching and it is spaced out, there is a certain voltage drop. But as we know, voltage drop is not only resistive, it is also reactive. So there's inductance and capacitance coming into play here. They provide a value of volt drop in millivolts per amp per meter, and you multiply this value by the design current and the length and AS, because we are in millivolts, you connect to volts and we get a value. I'll show you an example. Let us consider a situation 35 square mm 4-core cable. 35 square mm 4-core cable. Z is the total impedance value, 1.2 milliamps per millivolts per amp per meter, like I just mentioned here. So for a 50-meter three-phase circuit, if we are considering 35 square mm conductor, 90 amp load current on a 4-core, 50 meters times 90 amps times 1.2 millivolts per amp per meter, which is correct from millivolts to volts, we get 5.4 volts. This is how we calculate volt drop from manufacturer data. There is a far more interesting calculation given, in IEC 60364. It's just an explanation of really what is being done here, and it provides you a more, I wouldn't say accurate value, it provides you a more holistic picture on how it is calculated. The manufacturer data is just based on this formula itself. So in the absence of manufacturer data, you can use this formula. But really, if you are using any decent conductor, manufacturer's cable or conductor, you will get these values anyways. Now, there are three-phase circuits supplying single-phase circuits. How do we deal with this voltage drop? So I'll illustrate through an example. See, again, idea is that the final circuit is given the required voltage. So if I consider now two-phase drop between the three-phase circuit, 2 volt drop between the three-phase circuit here, and a 2.3 volt drop between the circuit here, I cannot just add 2 volt and 2.3 volt and get 4.3 volt, because this is a three-phase volt drop. This is a single phase and neutral volt drop. So there are two things. First thing I can consider is percentage voltage drop. 2 volts out of a 400 volt three-phase circuit is 0.5%. 2.3 volts out of 230 volts for one phase was neutral is 1%. So 0.5% plus 1.5%, which is plus 1%, which is 1.5%. So total voltage drop is 1.5%. Utilization voltage is 230 volt nominal. So 1.5% into 230 volt is having a total volt drop of 3.45 volts here. Other approaches, take the three-phase volt drop, divide by root 3 and add it by the single phase plus neutral volt drop. Same value we get. Now, other considerations. If you have an operating temperature, the cables are not being run to the full current carrying capacity, you can get away with the slightly lower voltage drop. And of course, power factor. Like I mentioned here, you have to take into account power factor anyways. And manufacturer data also do that. You have to apply correction factor. Now, the more I present this, the more questions I get about distribution systems. Like I can already see that there are some questions in the webinar chat. How do we calculate voltage drop in a distribution system? Okay, let's look at an example. So let's say you have 11 kilovolt, 433 volt transformer. Doesn't really matter what the primary voltage is for the cases of volt drop. What do we do? Step number one, we set a tolerance value. Now, if we look at the standard 60038, it talks about plus minus 10%. So for a 400 volt circuit, plus 10% is 440 volts, minus 10% is 360 volts. For a 230 volt circuit, this becomes 253 volts and 207 volts. So, what do we do? First thing, remember the idea is that the furthest point receives the voltage, because as the length increases, the voltage drop increases. So, what do we do? I set the transformer first. This is the same transformer. I'm just considering three phase here and single phase here to the highest possible setting given the tolerance. So, for a 400 volt circuit, multiply by 1.1, 440 volts. Set this transformer to 440 volts. And then I have a possibility of receiving between 440 to 400 volts here. I design the circuit such that I get the nominal value 400 volts at the most extreme point of commencement of supply. So remember, what I'm doing is I am designing for the furthest point of commencement of supply such that once the transformer is set to the highest value taken into account the tolerance, so 400 volt plus 10%, I am getting 400 volts here. Same case here, 253 is the highest value I can go to take into account a 10% tolerance, and I want 230 here. So I designed this circuit such that I get a 10% volt drop in the actual distribution circuit, the distribution system. Then within the installation is very simple. I can decide whether I want to do 3 volt or 5 volt or 6 volt or 8 volt depending on my equipment, and I allow this voltage drop within the actual circuit. So again, I would like to illustrate. The idea is that we can get the nominal voltage at the furthest point, so whether that be 400 or 230, and I have to make sure that at the closest point to the actual transformer, I do not exceed this tolerance. Because see, the transformer may allow me to go over 440. But if I do that, I am exceeding the 10% tolerance that I had initially set here, whether that be 440 or 253. So I am designing for the furthest point, but I am ensuring that the tapping is not set such that the voltage available at the closest point to the transformer does not exceed the maximum voltage allowable. Normally, like I said, we think about the lowest voltage because it's voltage drop, but because we are designing for, say, a very long run, we need to ensure that the furthest point, the closest point of utilization does not have a voltage exceeding the maximum, taking into account the tolerance. Now, neutral conductors. The size of the neutral conductor has to be equal to the size of the line conductor in a single phase two wire circuit, obviously. For a polyphase circuit where the conductor is less than 16 square mm copper or 25 square mm aluminum, and where the neutral conductor current does not correspond to the line conductor current. This is very common. We triple and harmonics. Anything in excess of 15% will cause a significant current in the neutral. Therefore, it's no longer balanced. This is an image to show you a 3.5 core cable, which we really should not be using anymore. Reduced cross-sectional area are permitted, yes, but because you can never really get the neutral conductor current, including harmonics, to be lesser than the cross-sectional area, then half the line conductor cross-sectional area. So yeah, good luck. Harmonics. The most significant one are triplet harmonics. Um, so we talk about red, yellow, blue. Okay, phase L1, L2, L3. Because we have equipment like electronic control and power supply equipment, this results in non-sinusoidal load currents, distorted load currents, and there are further waveforms superimposed on the fundamental waveform. These are in multiples of the fundamental waveform. So this is a 50 hertz. This may be 150 hertz, for instance. Thing is, normally, if they're 50 hertz and they're all 120 degrees apart, they will all cancel out. However, because these are times three, they will sum. So effectively, we have a super. We have my apologies. We have this adding, and we have currents flowing in the neutral conductor current. Reduction factors for harmonic currents between 5 to 15% harmonic content. We select the cross-sectional area based on the line conductor current and apply no reduction factor. Between 15 to 33%, we select it based on the line conductor current and apply a reduction factor of 0.86. Between 33 to 45, also 0.86 reduction factor. However, now we are selecting cross-sectional area of the cable based on the neutral conductor current. In excess of 45%, neutral conductor current, but we do not need to apply this reduction factor anymore because we have oversized it that significantly that the reduction in we will no longer utilize the line conductors to their full current carrying capacities, and that is offsetting the heat generated by the neutral conductor running at their full current carrying capacities. Um, like I said, these are the factors. What does this look like? So if we consider 100 amps, 15% total harmonic distortion. Okay, I'll re-explain the slide in that case. Depending on the triplet harmonic content, we have decided to first decide whether we want to select the cable's size based on the line conductor or the neutral conductor. Once we decide that, see, between 0 to 33%, we decide on the basis of the line conductor current. Between 33 to 45 and excess of 45, really, in excess of 33%, we get the cable has to be selected on the basis of the neutral conductor current. Now, like I mentioned earlier, I will just go back. Conductor current carrying capacity is based on the number of loaded conductors. So for a three-phase circuit, it is three loaded conductor and but we actually have four loaded conductors because it is only considering line L1, L2, L3, but it's not considering the neutral being loaded. Because we are now in effect grouping a fourth loaded conductor with this circuit, a reduction factor has to be taken into account to come up with the current carrying capacity. That is this 0.86 value that I showed you here. Now, like I said, this is the value to choose. When we have conductor currents between triple harmonic content between 15 to 33%. As you can see, if there is 33% triple harmonic distortion, the neutral conductor current is 99% of the line conductor current. So almost the same as the line conductor current. In these cases, because we are effectively having a fourth grouped conductor, therefore this 0.86 value takes into account this presence of the fourth grouped conductor. The cross-sectional area of the neutral conductor has to be considered if the current in the neutral is exceeding the line conductor current, because if you consider anything in excess of 33% or say 30, even 34%, right? 34 into 3, 102%. 102% current flowing in the of the line conductor flowing in the neutral conductor. Now, not only do you have to consider the fact that there is a fourth grouped conductor, you have to the current carrying capacity can no longer be decided on the basis of the line conductor current, because the more amount of current is actually flowing in the neutral conductor. So it's based on the neutral conductor current and the radiation vector supplied. We need to now select on the basis of the neutral conductor current, but not apply this duration vector if it's excess of 45%, because the line conductors are no longer running to their full current carrying capacity. Therefore, this 0.86 can be forgotten about, but still current has to be selected based on the current flowing in the neutral conductor. I understand that this is quite new, and perhaps the slides are relatively simple. That has been very deliberate because I spent quite a lot of time deciding whether to go complex or simple. And what I realized is that the subjects are simple. When we come to example calculations, that is when things can get tricky. So, which is I've tried to show you some examples. But if you feel that at any point that the slides are too simple, after the webinar and the slides are complete, we'll allow you to unmute yourself and ask a question, and then I can address your specific concern on the specific slide as well in a more detailed way. This is just an example calculation for the previous table. If we consider 100 amp current in the line conductor and 15% tripling harmonic current, that is basically times 3, 45 amps flowing in the neutral. We decide the current on the basis of the line conductor. We consider only 100 amps. If it is between 15 to 33% and we consider 33%, 33 times 3 times 100 is 99 amps. We do 99 divided by 0.86. Now you have to consider a 160 amp current in the line conductor. 100 amp current, 45% triple harmonic distortion means 135 amps will flow in the neutral. Now we can no longer select the current on the basis of the line conductor current, because the cable has to be selected on the basis of the neutral conductor. So we do 135 divided by 0.86, we get up to 157 amps. So the current IZ value that we are looking at is 157. In excess of this, same story there, but we do not apply this 0.86 value because, like I said, the current flowing in the line conductors is such that it is not no longer to the full current carrying capacity of the line conductor. So we can forget about this 0.86 factor. Look at an example calculation. If we consider a 250 amp load, 40% total harmonic distortion due to triplet harmonics, 40% into 3 is into 250 is 300 amps flowing in the neutral. Because we are between the 33 to 45% threshold, selection is based on the neutral conductor current. So we need to know the current in the neutral, 300 amps. 300 amp divided by 0.86 is 348.9 amps. So our our IB value, design current, on which the IN and the IZ value is selected, becomes 348.9 amps. Further calculations, harmonics not only affect current carrying capacity, but even voltage drop. So this is just an example. Again, I'm not going to go into too much detail about this because we want to keep things simple. You obviously, my job is not to teach you how to do electrical installations, but just to give you a picture on what you have to consider. The actual reading of the standard has to be done by yourself. It affects the cable ratings, voltage drop, work hour reduction, and equipment functioning as well. However, we only spoke about triple harmonic, which is third and multiples of third. If we have harmonics of the fifth, seventh order, etc., they even affect the line conductor currents. These are beyond the scope of the 60364 series. There are other standards to look at for these. Now, what value of the total harmonic distortion do I consider? As a rule of thumb, 70% for electronic equipment like televisions, computers, printers, photocopiers, etc. 30% THD for fluorescent lighting. 15% for adjustable speed drives, so on and so forth. So yeah, very normal, 70% in IT equipment. Okay, now earth fault loop impedance, everybody's favorite subject. The idea, like I mentioned, of earth fault loop impedance is that is the device going to cause disconnection in the required time such that protection against electric shock is ensured? Show an image. We consider this installation. This is our supply or our source. This is our conductor flowing in the distribution system. This is our installation, point of commencement of supply, excuse me, and conductor flowing from the point of commencement of supply to the load and the area, rather the area where the fault is. Rotative conductor flowing from the area of the fault to the point of commencement of supply back to the source. Our idea is that if a fault occurs here, the impedances of this loop, earth fault loop, so I call it earth fault loop impedance, has to be low enough such that the amount of current that will flow through will cause the device to disconnect in a required time. That time is given in NEC. It is zero point 0.4 seconds for final circuits in a TN system, zero point 0.2 seconds for final circuits in a TD system, 1 second for distribution circuits in certain final circuits in a TT, and 5 seconds for distribution circuits in certain final circuits in a TN. Don't focus on the time right now. The idea is loop impedance. Now, what does this mean? The current flowing causing disconnection in the required time times the loop impedance shall be lesser than or equal to the nominal voltage. So, you know this. We apply, so there are a variety of safety factors taken into consideration across the world. In India, we consider two-third, which means if we're supposed to have one, say zero point 0.8 ohms, I'll give you an example calculation. For instance, assume that this breaker is a B6 breaker, which means it requires 6 into 5, which is 30 amperes to disconnect instantaneously. So IA is 30, UO is 230. So 230 divided by 30 is 7.67 ohms. Multiply by that by a two-third factor, and we get 5.1 ohms. I'll give you a better example. If this was, say, a 100 amp device where disconnection was happening at times 10, 1000 amps, 230 volt divided by 1000 amps is 0.23 ohms, and we apply a two-third correction factor, which becomes 0.153 ohms. What is an example calculation? How do we ensure that this value is not exceeded? Remember, we measure earth fault loop impedance as a part of verification. However, it's not okay to just erect the installation and then say, oh my God, you know, I should have selected a bigger cable. This has to be calculated at the design stage. So we'll consider a very simple example, conductor smaller than 16 square mm. Consider 400 230 volt TNS system. Zero point 0.5 ohms is the value of ZL plus ZP plus Z sub, the measured value of earth fault loop impedance at the point of commencement of supply. I have 2.5 square mm line and PE conductors. These are running for 15 meters from the point of commencement of supply to the last load. Circuit is rated by a B16 MCB. Okay. I look at 60228 in India, IS 8130. I know for a 2.5 square mm copper conductor, it will have a resistance of 7.41 milliohms per meter. I have a line and a neutral, so R1 plus R2. So line and a protective earth, 7.41 milliohms per meter plus 7.41 milliohms per meter, multiplied by 15 meters. And I'm just correcting from, this should be, sorry, milliohms. So 1 ohm per 1000 milliohms. We get 0.2223 ohms. That is the value of basically Z1 plus Z2. Add this to the earth fault loop impedance measured here at the point of commencement of supply. So Z sub plus ZL plus ZP is 0.5. Z1 plus Z2 is 0.2223. So zero point 0.5 plus 0.2223 is 0.7223. What is the maximum allowable ZS? Well, 230 volt is a circuit, single phase circuit. 16 amp is the breaker. So B16, so times 5, we get 1.91 ohms. So 0.7223 is lesser than 1.91 ohms. We are happy. Our loop impedance value is satisfied. Now, like I said, for cables up to 16 square mm or lesser than 25 square mm, instead of Z1, Z2, we can consider R1, R2, the resistive component. This is what I've done here. However, this cannot be done if we have bigger cables or if we have armored cables. Now, this is going to be a very interesting slide. I'll show you a picture here and I want you to go on a story, a little bit of a story with me. I have an MCCB, I have an isolator, and I have a load air conditioner. It's a three-phase circuit. I'm using a steel wire armored cable. Okay. I have glanded at both ends as I should, and the armor is my protective earth conductor. Now, there are two practices in the industry. Practice number one is that the armor is used as the protective earth conductor. Practice number two, the armor is used in excess with a parallel conductor as well. In this case, the armor is also part of your Z2 value. Now, not only do I have to consider the effect of the armor, I have to also consider that there is a certain inductance, there is a reactive component to it. So, how do we calculate the earth fault loop impedance? Now, remember we have to break up the reactive component and the resistive component because we know that the impedance is equal to the square root of the resistance squared plus the reactance squared. Because in smaller cables, the resistance is the significant part, the reactance is almost nil. We can assume X is equal to 0 and we just get Z is equal to approximately R. But in larger cables, especially when you look at steel wire armored cables, this is a concern. So what do we deal with? Remember, break it down into the resistive component and the reactive component. The resistive component, first thing we do is we take milliohms per meter for the loop of R1, R2 or C1 FH, PH, and we add it to the value of the armor. So this is the case where only the armor is used as the protective earth conductor, not the armor and a separate conductor. For the phase conductor, we take the value like we have always done. We add it with 1.1 times the resistance of the armor. And this is our R1, R2. So phase conductor plus 1.1 times the armor. Multiply this by the length, multiply this by 1, divide by 1000 effectively to get our resistive component. I'm repeating, earlier we did R1, R2, but they were both copper conductors, so we just did 7.41 plus 7.41. If the armor is used as a protective earth conductor, you cannot do 7.41 plus 7.41. You have to do 7.41 plus whatever this value is for the armoring. I'll show you an example calculation. And we multiply this value by 1.1. Multiply by the length, simple. The reactive component we assume as 0.3 milliohms per meter. Multiply by the length, multiply by the correction factor just to convert from milliohms to ohms. Simple again. Then what do we do if we have a armor plus a parallel conductor? Like I said, armor plus a parallel conductor. What do we do is quite simple. We follow the same loop. So line plus P, line is just the core. PE is now the value of the core plus, sorry, not the core, the armor plus the parallel conductor, RP, we multiply by 1.1. Here, instead of zero point 0.3 milliohms per meter, we take zero point 0.4 milliohms per meter. The question is, how do we now calculate this RP? So here we do not multiply by 1.1. Here, I'll show you why. We take simple line plus the parallel, the overall impedance, the overall resistance of the parallel conductor plus the armor. The 1.1 has only been multiplied by the value of the armor, not the actual parallel conductor that is running. RP, which is the parallel, which is the effective resistance of the armor in parallel with the parallel conductor, is calculated by 1 divided by 1 upon 1.1 RA, which is the armor, and 1 upon R of the resistance of the protective, this is the parallel conductor. The 1.1 value only is multiplied to the resistance of the armor. That was the mistake that was here, by the way. 1.1 has to only be multiplied by the resistance of the armor. And like I said, instead of zero point 0.3, we take zero point 0.4 here as the reactive component. Let's look at an example calculation. Consider earth fault loop impedance external is zero point 0.2 ohms here. I have 50 meters of a 35 square mm 4 core copper conductor, steel wire armor. I have a 63 amp MCCB set to trip instantaneously at 5 times the rated current. First step, calculate what is the maximum earth fault loop impedance permissible. 230 divided by 63 times 5, 40.48 ohms. This is the maximum earth fault loop impedance I am allowed for the device to trip in the required time. Okay, now, how do we come up with the resistances? 35 square mm conductor. Copper conductor is 0.524 milliohms per meter. Steel wire armor, 4 core cable. Resistance of the armor is 1.9 milliohms per meter. Okay. Now, you will notice that these resistances are at 20 degrees Celsius. However, when the cable runs at maximum operating temperature, the resistances are higher because of the temperature. So there are certain correction factors taken into account. 0.524 milliohms per meter is the value for the core. We multiply this by 1.2 to get the 70-degree value. 1.1 times 1.9, which is the value for the armor, has to also be multiplied by 1.225 to consider that the armor is now also at 70 degrees. Multiply by 50 meters, go from milliohms to ohms, we get 0.160 ohms. The resistive component is not taken care of. The reactive component, 0.3 milliohms per meter. Remember, no parallel conductor. Multiply by 50 meters, 0.015 ohms. Z1 plus Z2 is equal to square root of 0.160 squared plus 0.015 squared, 0.161 ohms. External earth fault loop impedance is 0.20. So 0.20 plus 0.161 is 0.361 ohms. Simple. Now, how do we protect our cable against short circuit currents? We've sized our cables for current carrying capacity. We've sized our cables for voltage drop. We've also sized our cable to ensure that the earth fault loop impedance such that the device disconnects for protection against electric shock. But can the cable now withstand the current for the required time? Well, for cables and insulated conductors, the standard says that all current caused by a short circuit occurring at any point of the circuit shall be interrupted in a time not exceeding that which brings the insulation of the conductors to the permitted limit temperature. If you remember earlier, we spoke about normal operating temperature and limiting temperature. Limiting temperature is the temperature that the cable achieves during a fault for how many ever milliseconds or seconds. If we look at the same diagram again and we now consider a line to neutral short circuit, I have the Z, so supply impedance. I have the line conductor to the point of commencement of supply, the neutral conductor to the point of commencement of supply, and the line conductor to the point where the short circuit occurs, and the neutral conductor to the point where the short circuit occurs. I calculate the prospective fault current by first calculating what is the line to neutral loop impedance at this point, because that will determine the magnitude of fault current. So, quite simple, ZLN plus R1 plus Rn, or Zn plus Zn. I have not taken Z1 plus Zn simply because I do not want to overcomplicate things, but you get the picture. The same, you need to take into account both the resistive and the reactive part of it, so to get a overall impedance. The adiabatic equation tells us that the time in which, in seconds, so which a fault is interrupted, shall be equal, well, the time has to be lesser than or equal to k squared h squared by I squared. What is this? K squared is a coefficient given in the standard. I should have the coefficient. Why do I not have the coefficient? It's here. These are given. So for a PVC cable up to 300 square mm, we consider 115 for copper, 76 for aluminum. For a XLPA cable, we consider 153 for copper, 94 for aluminum, so on and so forth. That is your K. S is the cross-sectional area in square millimeters. I is the fault current to be calculated based on this value. And K is, like I said, this factor. For faults that are interrupted within zero point 0.1 seconds, which are current limiting devices generally, we can rearrange this equation, and I squared T shall be lesser than or equal to K squared S squared. When you have faults interrupted within less than zero point 0.1 seconds, manufacturers will give you graphs quoting I squared T values, OCPT manufacturers. The electrical energy in a fault has to be less than the thermal withstand of the cable, and a cable will give a K squared S squared. Let me look at an example. Remember, all this is for all short circuits occurring. So, for earth fault loop impedance, we only considered the fault here. But for short circuit, we need to consider, for withstand or short circuit, we need to consider all values. So, and the best way to do that is graphically. Like I said, manufacturers will give you this I squared T graph, showing you for this amount of fault current, this is the amount of I squared T. Look at a sample example. A load is protected by a 32 amp B curve 60898 MCV. The measured line to neutral impedance at the origin of the circuit here is zero point 0.1 ohms. Length of the cable required from the origin of the circuit to the load is 45 meters. 6 square mm conductor is being used, class 2. Perform a thermal stand analysis to determine if the cable is suitably coordinated. Okay, we know at this point 0.1 ohms. What is the short circuit current here? Single phase short circuit current, 230 divided by 0.1 ohm, 2300 amp. That is the maximum possible short circuit current. What is the short circuit current at the extremity? 3.08 milliohms per meter. Here we are not considering an armored cable, we are simply considering two copper conductors times 2 times 45 meters, that's the length of the run, times 1.2 to correct from 20 to 70, because like I said, the resistances are given at 20 degrees. Correct from milliohms to ohms and add it to 1.1 to 0.1, which is the source. At the extremity, we have 0.43264 ohms. Minimum fault current, 230 divided by this value, 531 amps. So we have a range of currents, possible short circuit currents from 2300 amps to 531.61 amps. This is just an explanation for this thing. Resistance values of a single core cables, and since the line and neutral conductors both contribute to the resistance, this value is to be multiplied by 2. The resistances are given at ambient temperature 20 degrees, but the highest possible loop impedance at the extremity is when the cable is operating at maximum operating temperature, so 1.2 is taken into account. This is simple. What value of K do I choose? PVC cable, less than 300 square mm, 115 is the value I choose. So, what is K squared S squared? K squared S squared is 115 squared times 6 squared, which is 476,100 amp squared seconds. Now, let's plot this. This is our K squared S squared, which is also in amp squared seconds, 476,100. This is the value of prospective of I squared T released by the protected device. And this is the minimum short circuit current 531.61 amps and the maximum 2300 amps for all values such that between 2300 amps to 531 amps of short circuit current, k squared s squared is always less than I squared t because this graph is always lower than this point. Simple. And our equation, our withstand is taken care of. Where does it go wrong? Case number one, which is that this graph, this red line is always provided by the manufacturer of the OCPD, by the way, goes above the thermal withstand, which means for in this case, separate case, imagine maximum short circuit current is 7,667 amps. Over this certain value, I squared T exceeds K squared H squared. So the cable will be damaged for short circuit currents at this point. Option two is that the device is just not going to disconnect, and the amount of let through energy is so massive that the cable is not protected for values uh, for short circuit currents below this because the device will simply not disconnect. Anyways, that's a lot to digest, I'm sure, and it will take you some time. Remember, again, my job is not to teach you how to do electrical installation design, it is to show you the variety of factors that you have to take into account. You can only really learn from reading the standard and working through some examples yourself. And there are plenty of guidance, there's plenty of guidance and books available for the same. Anyways, this is the end of this presentation. We will take questions now and any closing remarks. Thank you.
Of all, some participants posted the question in chat box. So please post your questions in Q&A. Questions in the chat box will not be answered. It will be very difficult. So to start with, can you see the Q&A?
Yeah, I can see the Q&A.
Okay, the first question is from Mr. Ranganathan. What factors do we need consider in cable sizing for accounting harmonics?
Okay. I think this question was asked before we touched on the harmonic subject. So there are the factors like I already mentioned, like I that I showed you for current carrying capacity. However, there are also some other factors, like I said. However, these are beyond the scope of 732, 60364. So just give me one moment. I will tell you the number, the standard to refer to. I believe it is the six. One moment, just hold on. I also open the annex to show you. There is information provided in the 60287 series, specifically part 1-1 and subsequent parts that talk about this. Also, there are for harmonics, there is the values of disturbances that are provided in the 61000 series of standards. Um, I'll just open the annex in 732 that show the details on harmonics so you can read through. The Annex 5, effect of harmonic current on balanced three-phase systems, page 204.
You can make the screen a little bit bigger.
Sure. So Annex 5 in IS 73 talk in details of the effect of harmonic current on balanced three-phase systems with an example calculation as well. Where is it gone? Yeah, there. So I hope that provides you some guidance, Mr. Ranganathan. Okay. Next question.
How to do cable sizing for single core cable for higher kilowatt motors? I think this
Uh,
question also asked before you answered protection of conductors in parallel. Probably you can answer
yeah.
that.
Yeah, it is the same. However, I will just share the screen again and show you some slides that I did not show you on purpose. See, there are other concerns when cables exceed 50 square mm and when these cables have metallic sheaths which are non-magnetic. We need to ensure that the sheath voltage, if they are bonded at a single point, does not exceed 25 volts and the sheath voltage does not cause corrosion. If you bond on both ends, you are going to have currents flowing within this sheath, which is going to reduce the overall current carrying capacity. So there are calculations given for the sheath voltage. You can find further information in the 60287 part 1, 1 and 1, 2 on this information. Um, you need to now calculate these sheath voltages to ensure that they do not exceed 25 volts and if they and also that they do not cause corrosion. The values are dependent on the configuration of cable, whether they're touching, spaced, or in trefoil, single phase and three phase. These values are calculated here as just an example I've shown you, but you need this information from the manufacturers because to run these calculations, you need manufacturer data. This is not mentioned in the Indian product standard. So just keep that in mind. You need manufacturer data. These are just some sheet voltage calculations just to show you. So, these values do not have to exceed 25 volts. But ideally, the sheet voltage has to be below 12 volts because studies have shown that that is a much safer value. Additionally, if we look at IS 732, you will notice that current carrying capacities for single core cables are provided based on certain spacing, touching horizontal spacing of one diameter and vertical spacing of one diameter. When you increase the spacing between cables, the reactance increases. So if you look at the ratio of actual spacing to tabulated spacing, there is an increased reactance that has to be taken into account as well. This is a very vast subject and it's beyond the scope of the 60364 series or NEC or 732. Please refer to the 60287 series for this. I hope that answers your question.
Yes.
Next question. Yeah.
How many hours I2 should calculate it? Some code said 4 hours.
So that is dependent entirely on the actual product standard. So let me show you uh, what product can I show you? Uh, instead of doing that, I will just show you the slide I have. This is an excerpt from the product standard. I2 is calculated on the basis of conventional time mentioned in the product standard. The reason this value increases as the rating increases is that when you use a higher size cable, they can withstand an overload for slightly longer. So you don't have to calculate I2. I2 is given to you by the manufacturer for a given time. You don't need to do any calculation yourself. Unless, of course, it is an MCCB, then you need to look at the graph and figure and then figure it out. Again, refer to the product standard.
Yeah. Okay. Then there is an interesting question. Should we place HV cable on top tier of with respect to LV cable or LV cable come on top tier? That means if there are multiple, no, two tires of two levels of cables running in one route, HV is at the top or LV is at the top is the question.
Well, I don't know because I'm not a HV person. Perhaps you can answer that question.
Okay. It depends on the application. Only thing is it depends on your convenience. In fact, the only thing is the necessary space has to be kept. The spaces are, I think, it is available in the standard. So the next question: what is the difference in private supply and public supply? Does public supply means EB connect common supply point and private means individual consumers having its own? Yes, your answer is there in your question itself. Private supply means if you have your own transformer, public means you are getting supply from the utility company. Then why do we need why do we need restrict the voltage drop to 5% at the end load in industries?
Okay, interesting question. You don't. This is guidance. Guidance provided where you do not have information provided by the product standard. In an industry, you will know what the tolerance level is for the equipment. So then all you need to ensure is that this voltage drop does not cause a voltage lower than the minimum utilization voltage required for the equipment. But what you will notice is that if you choose a voltage drop in excess of 5%, in most cases, when you come to the fourth stage, which is the third stage, this earth fault loop impedance, you are not going to satisfy earth fault loop impedance anyway, so you'll have to upsize the cable. So, no, you do not have to restrict it to 5% in an industry. These values are guidance for when there is an absence of of information on the connected load, but in an industry that will not be the case. And like I said earlier, in a larger network, anyways, the consideration is for utilization voltage, not this 3%, 5%, so on and so forth. So, yeah.
Okay, now there are few questions regarding harmonics. I will
Okay.
combine all the questions together. Should we multiply the harmonic reduction factor along with the other derating factors? How to evaluate the harmonic current at design stage? How does harmonic current affect selection of OCPD?
Okay. Should we multiply harmonic reduction with other reduction factor? Obviously, because remember, I had specifically, oh, I have not put that here. Yes, of course, because this is to be considered for IZ. Uh, so yes, absolutely. You need to take into account along with all other duration factors. Yes. How to evaluate the harmonic current at design stage? You should have this equipment given to you, this value of harmonic current given to you by the excuse me, the manufacturer equipment. I'll show you a. Just give me a moment. I'll just unshare. For a simple light, abroad manufacturers give you these values. Hold on.
India also they give light
They
manufacturer give the
they
value.
give.
Yeah, but the only problem is the values are there, but there is no limit for the maximum value. And most of the time, uh, the values can be trusted is also a question.
Uh, That is
Okay,
quite
take it,
interesting. I will just
oh,
share the screen 1 minute. So, oops, that is not the screen I intended to share. See, for this LED bulb, they provided 120% total harmonic distortion. So, this equipment it has to be given, it has to be taken. Whether it can be trusted or not is like Mr. Goga Kumar said, a separate story.
yeah.
Yes, it does affect the selection of OCPD, obviously.
How to evaluate the harmonic at the design stage? Of course, you get the data from the manufacturer. How does a harmonic current affect the selection of OCPD?
Um, okay, good question. From a very interesting participant as well. Let me share the slides again. The question again, the question was, what was the question? How to OCPD? Okay.
Yeah, yeah.
See, you need to size the OCPD such that IB is lesser than or equal to IN is lesser than or equal to IZ. The IB becomes your current after the duration is applied for the factors are applied for harmonics. So IB is basically the current after harmonics have been considered. This is either the line conductor current or the neutral conductor current as decided, which affects the size of the protected device.
Okay, right, Krish? The
Yeah.
next, how fusing factor is correlated with protection device other than fuse?
Okay. Good question. See, the we I know we call it fusing factor, and but really there is no actual term given. It is fluid tripping, non-tripping, fusing, non-tripping. So for a breaker, it is simply the value of which it disconnects for during an overload. So pretty simple. Just disconnect. You just forget about the word fusing. Just think about conventional disconnection, a conventional tripping current. Just yeah, you're right. It's not limited to fuses.
Yeah. Uh, so there are some questions. Mr. Narottam Kumar, ambient temperature is normal temperature, normal atmosphere temperature or temperature of area where cable is installed.
Well, of course, the more whichever is the more onerous. So, or rather, if the cable is installed in an air room that is always air conditioned, then you don't need. But usually, if it is hotter inside, where the area cable is being installed, you have to consider the hotter temperature.
Ah, okay. Mr. Alkendra Singh, why neutral conductor double the size of live conductor are being used in data centers and other IT installation?
Okay, interesting question. Well, I think you know now why. Because if you have, where is my slide on harmonic? If you have IT equipment, you can have almost 70% total harmonic distortion. We even saw one light bulb had 120. Now, if we use this to calculate, 70 times 3 is 210. So twice the current is flowing in the neutral conductor as the line conductor. That answers your question.
Okay. Um, Somebody, an anonymous attendee is asking about bus trunking and all. This is not related to today's topic, so we don't take this question. Now we,
Actually, if I just may,
yeah, in
so
wiring, the decision of a bus duct instead of traditional cables for electrical distribution. That is a question related to the uh, regulation.
okay. No, I know. I think he wants to know about the factors to use for calculations. Actually,
Is it? Okay, how can we take a decision on the same? Which factor we need to consider for the same? Yeah, correct.
so I will show you something that um, I don't think that is present in. Basically, without showing you an actual standard, because I don't want to show you the standard because of copyright reasons, you'll have to purchase the standard. The values are dependent entirely on the manufacturer's data. So just keep that in mind. A lot of it is to do with manufacturer data. We can discuss. You can, yeah, just keep that in mind. Yeah, power
Uh,
can, yeah. I don't know. This is relevant to what we
can
spoke
be
about. Yeah.
saved by using harmonic filter because 13 numbers drive Rajesh Kumar Singh. The question is not relevant. Then Mr. Ashish Nema, is there any standard which provides permissible duration of overloading LV XLP cables with percentage overload current?
You're not supposed to overload the cable. Period.
Yeah, very simple answer. In a high-rise building, the decision to use a bus duct instead of traditional cables for electrical distribution, how we can take decision on the same, okay, this is already answered. One moment. Uh, there are some anonymous questions from anonymous attendees. So this we generally don't take. As we know from Mr. Kamalesh Kumar, as we know, AC resistance is higher than DC resistance because of skin effect. My question is that is skin depth is constant for a given cable material, irrespective of conductor diameter.
I would say to this gentleman, look at the 60287 series. There are several factors, including skin effect, taken into account there. Have a look.
Okay. What is the standard?
60287. I will just um, tell you which part also. I think 1 1 gives you. This is an entire series of standards available, and there are various factors provided. Not sorry, 1 1.
Can show the subject, Krish. Electric
Yeah,
cables of the current rating uh, equations, 100% load factor and calculation of losses. So it has to be based on this particular. The information is available in the standard. Am I correct?
yeah. There are factors that take into account skin effect in this standard, I believe.
Yeah. Sometimes, the accessing these kind of standards is a question, and probably there are some people, those who don't want to use any calculation from standards. Everything should be in Excel sheet and thumb. Truly, the answer is please look at the standard. You have the answer there. Then, Mr. Sandeep Gaikwad, can we route power, signal, and communication cable in single conduit pipe? Is there any effect on signal and communication cable?
Of course, there'll be an effect. In most cases, you should not do this
Can
because
you
there is
refer
separation. Sorry?
the clause which is
Yeah,
in
yeah, yeah, yeah. One moment.
go to 4.5?
It is in 4. Achha, yeah, it is in 4.5 also. Yes, 444. Yeah. Uh,
Below. Next. You can go a little bit faster. Yeah, next page. Probably next 2-3 pages. Yeah.
this one.
Yeah. That is the clause, and there are some explanations with pictures also in this particular clause. Yeah, here it is. So, gentlemen, please look at IS 732. The explanations are given in the IS 732.
Yeah, I have a look. 4.5.
Yeah. Now we go to the next question. SWA can be enough for protective conductor. Some code accept that, but other country refuse it in some certain sizes, and we need to have additional protective conductor. Similar the calculation you showed. Okay, this is not a question, it's a statement.
Actually, I would like to address this question. Whether or not the armor can be considered as a protective conductor is dependent on whether it is terminated properly. But we are required to terminate it properly. If it is terminated properly, there will be fault current flowing in the armor. So you cannot neglect that. Still need to calculate the fault current in the armor, and you still need to ensure that can the armor actually withstand that amount of fault current for the time it is subject to that fault current. So yes, whether country accept it or not, I cannot comment on. Like you said, it is a statement. But uh, regardless of that, we are required to terminate it properly. We are required to earth it. So we need to consider the effect of fault current flowing in the armor and how the current will either divide through the armor and a parallel conductor or flow through the armor itself.
Okay, okay, Krish. Um, so again, another question. In general, on ground reality in cable cellar room, all cables are loop and bunched together, and due to that, reactive current increases. Are you taking some factor into consideration while designing cable? In fact, we are not supposed to make these things into consideration. These are already explained in the standard, and we have to look at the standard and make a decision. Krish, you have any answer on this?
I would say that instead of designing the insulation for the bunched and looped up cables, lay the cable properly first, and then you design, and it should be designed for properly laying it. Of course, if you decide to talk about increased separation distances, that is a separate story, like I had showed you earlier. As a distance between the cables increases, reactance increases. But because they are bunched and laid poorly, we cannot just somehow make some compensation for it. You need to install properly.
Okay. So, what is the ideal tripping fusing time should be taken for an OCPD device for an application such as residential or commercial?
Well, residential or commercial, you will mostly use 60898 devices. So that there is nothing to take. It is already defined in the standard, and you can't really do anything about it.
Okay. Next is again anonymous attendee, so we cannot take it. Okay, can you explain more on thermal stability of low voltage cable?
Not sure what they mean.
Yeah, gentlemen, if you can come with a clear question, probably Krish can answer. Then 3000 next, Mr. Ranganathan, 3000 amps load current system has bus bar cable of higher size, where the same system with 50 kA requires lesser size. Oh, what?
I don't understand either.
We can't understand the question. What is cyclic loading factor for LV cable?
Uh, well, uh, I think you're referring to the fact that loads draw different amounts of currents at all times. But when we, not sure what cyclic loading factor is, because I've not heard
Okay,
that term
now
used in a
let's
standard. Yeah.
let's leave it. Let's leave it. If the question is clear, you can answer. Let's go to the next question. 3000 amps load current system has bus
Same.
bar
Oh,
cable of higher size, where the same system has 50 kA short circuit current for 1 second require lesser size. Why higher size is required for continuous operation? My goodness, gentlemen, I think there is some serious. Could you understand this question?
no, I cannot.
Yes, sorry for that. The question is not very clear.
Oh, okay. Wait, I think I understood what he's saying. I
Okay,
think his question is that why is the cable size, why are the cable being selected for fault current is not selected for continuous current carrying capacity? Obviously, because it is for fault current, the bus bar or whatever whatever conductor is being used. But again, not very clear. Yeah.
okay. How much is the harmonic level for a normal cable which would be good for power distribution system?
Well, I'm tempted to say zero, but it's not practical.
Yeah. So uh, that's all, Krish. Almost all the
One
questions.
interesting question, actually.
Yeah.
What factor should be considered during low voltage cable fault? What is the temperature effect of temperature? Very interesting question. But as I mentioned earlier, we need to consider maximum operating temperature. So during a fault, we consider the cables are at 70 degrees. There are some standards. There are some countries that
Can you
take
unshare
into
your?
account. Yeah,
Can you?
sure.
Yeah. Yeah.
There are some countries and there are some standards that look at different values. They look at conductor resistance at limiting temperature, conductor resistance at a temperature between limiting temperature and maximum operating temperature. It really depends on the protective device and how quickly it is able to disconnect. I think I know the gentleman that asked that question. So, yeah, I think he already knows the answer. But yeah, in most cases we take 70 degrees.
Yeah. Okay, okay, Krish, there is no one interested raising the hand for talking. I just put Apausar also in the group. Apausar,
Sure.
any?
Okay.
Good morning. Good morning, sir.
Morning.
Krish, it's a wonderful webinar.
Thank you very much.
Gopa has also. Am I audible? Am
Yes.
I,
Yes. Yes.
ah, Gopa has also conducted by answering and supporting to your webinar. Regarding, there are some more questions, especially people are dealing with bus duct, etc. They have to be dealt with in a separate, not with the cable. So that is related to the fire safety measures in multi-story building and CA regulations, for which the Gopa sir has rightly answered. And regarding one question, one person has raised the question of sizing, short circuit rating sizing. Is one for 1 second or 3 seconds? See, it's all dependent. It is the short circuit rating. I square T is equal to K square S square. It is limited adiabatic condition. That means less than 5 seconds. So we can't design a cable for 5 seconds. So practically we can resist the fault within 3 seconds. So it is 3 seconds or 1 second, depending upon your fault clearing device. The concept is the conductor should withstand the fault before the clearance of the fault. So cable is not a standalone factor. It is to be designed in coordination with several factors, most importantly the OCPD. So the OCPD in turn is dependent upon the clearing duration, fault clearing duration, for which your cable should withstand. So normally 1 second for downstream, and worst case to maintain the supply continuity, it can be 3 seconds as well in certain installations. So this is a basic thing only we have to observe while selecting a cable. It doesn't mean that you provide 3 seconds for all the main very high rated, for example, a solar PV fed, inverter fed cable. If anything goes wrong, it can be operated within 1 second. So it all depends upon the designer and the application in the field. So that's what I want to convey. So it's a very nice interaction from the participants as well. Thank you, Gopa, and thank you, Krish.
Thank you, sir. Thank you very much. So with this, we would like to close today's webinar. I hope the information was quite useful. So we will come back to you next week with another webinar. Probably the subject of next webinar is a panel discussion on the CEA regulations. Apau sir, next week if we
Yes, sir.
are
Okay, sir.
can
Okay, sir. We will do it.
yeah, there were we can also add a few more panelists so that this subject can be taken up. There were
Yeah, we will discuss, sir. We will discuss. We can add a few more people.
yeah.
So the topic is freeze. We can freeze the topic and we can announce a panelist
Yes,
in our
yes.
brochure.
Yeah. Thank you. Thank you. Thanks to all. Thank you very much. Thanks, Krish. If you have any points, you can also share the customer's final.
No,
Yeah.
no, nothing else. Just hope it was useful. Yeah.
Thank you. Thank you.